You know, our whole world runs on machines that play with energy, from the engine in your car to the AC unit in your window. But what's wild is that they all have to follow one single unbreakable rule. So let's dive into the first law of thermodynamics.
Have you ever really stopped to think about how an engine turns a little bit of fuel into actual physical motion? Or how an air conditioner does the exact opposite, using power to pull heat out of a room? Turns out they're just two sides of the same coin, and they're both governed by the universe's most important accounting rule.
And that rule is the first law of thermodynamics. Now, don't let the fancy name fool you. Behind all that is a surprisingly simple idea. At its very heart, it's just the universe's ultimate rule for keeping the books on energy. This one sentence says it all. You can't just make energy out of nothing, and you can't make it disappear either. All you can do is change it, transform it from one type to another.
Now, this might sound familiar, and it should. It's basically the law of conservation of energy, but it's specifically applied to stuff involving heat and work, which is the core of what thermodynamics is all about. This is the law that totally bursts the bubble for anyone dreaming of a perpetual motion machine, because it makes one thing crystal clear. You can't get more energy out than you put in.
Okay, so how do we actually write this rule down? Well, scientists and engineers talk in the language of math. So let's take a look at the beautifully simple equation that sums this whole thing up.
Yep, that's it. The whole law. Right there in 5 little characters. Delta U equals Q minus W. It might look almost too simple, but believe me, this little formula is the key to understanding just about every engine, power plant, and refrigerator on the planet. So, let's break down what each part really means. Honestly, the best way to think about this is like an energy budget. It works just like your bank account. You've got a balance, you've got deposits coming in, and you've got withdrawals going out. This equation is doing the exact same thing, just for energy.
So let's meet the 3 key players in our energy budget: the internal energy of the system, the heat we add to it, and the work that it does. Getting these 3 down is everything.
First up is delta U. The delta just means the change in, so this is the change in the system's internal energy. You can think of this as all the energy locked up inside a system, which you can usually feel as its temperature. In our analogy, this is your account balance. The equation tells us if that balance is going up or down.
Next, we have Q, which stands for heat. This is energy that's on the move, flowing from a warmer place to a cooler place. When heat flows into your system, that's a deposit into your energy account. Ka-ching! Your balance goes up. And finally, there's W, for work. This is the good stuff, the useful energy that the system actually puts out to get something done. Think about steam pushing the lid off a pot. That's work. In our budget, work is a withdrawal. You're spending some of your energy to make something happen, so your balance goes down. Okay, so we've got our budget straight. The change in your energy balance equals the deposits you put in minus the withdrawals you take out. Let's see how this plays out in the real world with our engine and our air conditioner.
So check this out. On one side, a heat engine takes a big energy deposit in the form of heat, or Q, and makes a withdrawal as useful work, W, to move the car. On the other side, the air conditioner does the complete opposite. It takes a deposit of work, from electricity, to force a withdrawal of heat from inside your room.
When you look at it this way, the relationship is super clear. The heat engine's goal is motion, so it turns a heat input into a work output. The air conditioner's goal is cooling, so it uses a work input to move heat. They have totally opposite goals, but they both have to obey that exact same energy budget. No energy is ever magically created or lost, it's just transformed and moved around.
So, this law is obviously incredibly powerful. It's fundamental. But, and this is a really big but, it's not the whole story. It has a very specific job to do, and there are some huge questions it just can't answer.
Let's go back to that bookkeeper analogy. A good bookkeeper can tell you if your accounts are perfectly balanced, right? But they can't tell you if your business idea is actually going to work. The first law is that perfect bookkeeper. It makes sure the energy numbers always add up, but it has no clue whether a process is even possible in the real world.
So let's make this crystal clear. What the first law is a fantastic energy accounting tool. It confirms conservation, full stop. But what it is not is a fortune teller. It can't predict direction. For instance, the law wouldn't forbid heat from flowing from your ice cube into your warm drink. The energy books would still balance. But we know that's absurd. It never ever happens. And the first law has no idea why.
All right, so what are the big takeaways here? First, energy is always conserved. Always. It just changes its clothes. Second, that simple little equation, delta U equals Q minus W, is the key to tracking all those changes. And finally, remember that this one simple law is the foundation for almost all the technology that powers our modern world.
And all of that leaves us with one massive lingering question. If the first law is just about balancing the books and energy is never really lost, then what is the deeper rule that forces change to happen in one direction? What's the cosmic traffic cop that tells heat it must flow from hot to cold and never the other way around? Well, that is a question for the second law of thermodynamics.